Hi, welcome back. So in the last talk, we stopped at the topological interpretation of an L2 harmonic one form. So basically, they are represented by the non-peripheral surfaces. And the natural corollary of this topological interpretation is that the Thurston norm is a genuine norm on the L2 harmonic one form. So remember, the Thurston norm can be degenerate when you have tori. Just like in a three torus, the Thurston norm is trivial for those essential torus. But now the non-peripheral surface tell you, okay, you don't need to worry about that. The Thurston norm is going to be a genuine norm, so it's going to be non-trivial for non-trivial L2 harmonic form. And then with this good property, a natural corollary, geometric one, is that the least area norm is actually controlled by the Thurston norm, just like the closed case. Remember in the closed hyperbolic field manifold, by the work of Uhlenberg, it tells you a stable minimum surface has its area bounded below and above by the genus. Now, this is not something you would expect in a flat manifold, because remember, because our three torus friend has a flat two torus, this flat two torus, its genus is always one, but its area can be like arbitrary depending on your manifold, because you can stretch this three torus in many different ways. So those two torus would have the same genus, same topology, but very different area. And also in terms of Thurston norm, the Thurston norm of the torus would be zero, but then the area will be definitely non-trivial, like area will be one in this case, considered like a unit square. So this least area norm bounded by the Thurston norm is already a reflection of some like rigidity of the hyperbolic manifolds. In the cusp case, this is also true, as I said, by the fact that it's non-peripheral. Then this inequality generalized Uhlenberg's observation first appeared in Haas, and also in Colin Hothworth, Maze, and Rosenberg, 2014, they also discuss such area estimate, which is a lower and upper bound for the area. But then one crucial property for the least area norm is that it must make sense, because we need an embedded surface representative realizing the least area norm. And that's done by Huang and Wang, 2015, tells you that in the cusp manifold, so this is my cusp manifold, what you can do is that you can cut off the manifold at a height relative to the maximum cusp, let's say tau, and you get this compact core. This compact core not only contains topologically the non-peripheral surfaces, like my non-peripheral surfaces sitting inside here, but then geometrically to be this area, it might go out like this. So it might reach out to infinity, the least area one. But then when one tell you, okay, this cannot happen by some area comparison. So basically, some tau would contain all the representative. So you have a phi in the L2 harmonic one form, of course, non-trivial one. And then it's gonna dual to a surface S, and if you insist that this has to be least area, then what you can get is that the surface S is containing m tau. So in particular, the injectivity radius restricted to your least area representative of the L2 harmonic form is gonna be bounded from below. So it's not gonna be zero, because like those tori going to infinity. That's a good thing. And what I prove is that the L2 norm, just like the compact case, is bounded below by pi over root of volume times Thurston norm. So this part is basically similar to broken down field after an interpretation of the alto harmonic line form, an interpretation of its topology and geometry. And upper bound is slightly more complicated. The systole term is similar to the injectivity radius term. The systole is basically short to geodesic in the compact part or in the whole manifold. This term over here, you have a d. This is the diameter. You can think the largest diameter of the boundary tori of your maximum volume cusp. So the good point about this up right hand side is that the systole and the diameter term are independent of the m tau. So it's independent of how you truncate the manifold. The m tau, this tau will depend on the data on the boundary of the maximum volume cusp. But the injectivity rate of the m tau is very difficult to compute in general because you don't know how large is the tau, and then it's not clear that how you can come with formula for the injectivity rates of the m tau. So it is it takes more work to compute that invariant compared to systole and the diameter term. As a natural corollary is that if you consider a filter like use volume, then consider all cusp manifold with volume fixed bounded from above by this constant. You know that the alto norm is bounded from above by the first one up to the systole constant. The moral here is that the systole term almost always dominates the diameter term. Why is that? Because let's say you have a manifold M such that this diameter term will dominate, so it's larger than the systole term. But then if you have more than one cusp, you do then filling on the non-diameter cusp, then for large enough then filling coefficient, you would have a short enough geodesic so that the systole term will dominate back. And so except for finite many, the systole term will always give you a larger coefficient compared to the diameter term. Right. So that's about the systole. And then if you want to know about the technique, then for the closed case, in broken down field, what they did is that you consider this short Margulis tube. So this is my solid torus with a core geodesic being a simple closed geodesic. If you lift that the upper half space model, it is like this. And then you might have, if you intersect the whole thing by a ball of uniform radius, let's say a ball of radius mu over 2, mu is equal to 0.29 by Coulomb and Shalen 2012 for the Hawking manifolds. And then in particular, you might have many different copies because this epsilon, this short geodesic, let's say, its injectivity rate is epsilon. And then you would have approximately mu over epsilon many copies of duplicates when you do the computation in Hilbert space. The computation in Hilbert space is basically a harmonic expansion similar to the Taylor expansion. Here is where they set the work from Minsky. So in the cusp case, if you apply a similar technique, what's going to happen is that it gives you a term with different order, because if you consider the orbit of points under the rank 2 parabolic isometries, then and you cover with a ball of mu over 2 radius, now it's going to cover quadratically many orbits, right? Compared to here, which is linearly many. So basically, it gives you a term of mu square of epsilon square. So that's and this here, this epsilon will be the injectivity radius of the m tau. Now the issue is that so you would have a 10 pi over root of injectivity radius of the m tau and some other term over injectivity radius of the m tau with different order. So with more tool, like from Maziel and Phillips, for example, So Phillips. Then what you get is that what they use is Bessel function expansion. And they have a like 2 pages computation of asymptotic of the harmonic one form using the warped product structure of the cusp, so that you can get good estimate near the cusp. And then what I use is some popular subharmonic functions and some estimate, asymptotic estimate. In the end, what you can prove is that you will get the diameter and systole term, which is much better than the estimate of order of a different order from the Broca-Canton field. So the tool I use, one more tool I use is that remember, like the motivation I talked about in the beginning is that I have data like this, like here this L2 norm is going to depend on geometry near infinity. Then I want to retract all those support near infinity so that it is concentrated on the compact subdomain of the manifold, which is exactly the m tau here. Then this is actually realized by the Poincare duality. So basically, you have in the closed case, you take a harmonic one form, and the beta a closed to form. One way to interpret the Poincare duality is that the following equality is true. So this S is dual to alpha. And now if you consider the cusp case, and you take the alpha harmonic like before, we also have the following inequality. Now again, the work is by first Mazzeo and Phillips. So you would have a decay. So as you go to infinity, let's say y coordinate is a coordinate for how far you are away from the compact core. Then as y go to infinity, then the harmonic one form would decay exponentially. So this lambda over here depends on the boundary tori. Then the second tool I use is that Yau's lemma. You can think of as a generalized Stokes theorem, which tell you that, okay, you have a non-compact manifold. So it's not compact. Okay, so it's not compact. And then you have an integrable, this is important, integrable codimension one differential form. So it's M-1 dimensional. And then thus the omega is equal to 0. Okay. So basically, with Mazzeo and Phillips, I get good control near infinity, and with Yau's lemma about Stokes theorem, I can show that, okay, if I ignore those parts, in the end, it's going to vanish if I do the integral. So basically, in this case, I can reduce the commutation on the whole manifold to commutation on a surface which has compact support, which live inside the m tau. So specifically, we fix surface due to alpha. So this surface S is taut. So you can interpret the taut surface as a surface which realize your topological complexity. So there's no actual component. So you're not disjoint union with like actual compressible sphere or compressible genus surfaces. It's the exact amount of topology you need to represent the cohomology. And then the L2 norms by definition, this guy over here. And then but this is a Poincare duality I just established. So basically, this is what I mean, that I have an L2 norm, which depends on data near infinity, and then I can concentrate the computation on surface S. The surface S is a nice closed surfaces, right? So I can concentrate all those data on the surface. And this inequality is basically if you integrate a function, it's less than integration of its absolute value. And this inequality is basically, if you integrate a function, it's less than its maximum. And this is the natural linearity of integral. And this one comes from, we pick the top surface representative. So the area of S is bounded by 2 pi times genus 2 pi times g minus 1 of the surface. But if the surface is taut, then this g minus 1 is gonna be the Thurston norm. So this 2 pi g minus 1 is gonna be the Thurston norm. So basically you pick the surface so that this Thurston norm would actually bound the area. I want to make a comment, which is that Luca and Stearns last year, November, they also obtained an inequality bounding L infinity norm by the L2 norm for the general dimension, real and complex. But the issue is that the constant is implicit. It is not like in this case where I tell you, okay, it's 10 pi over square root of systole or like some diameter term. It is an implicit constant. But the paper is a beautiful paper discussing some L2 Betti number. About the sharpness, remember the broken down field tell you the pi over volume root times L2 norm is bounded by the Thurston norm. So in particular, it's a natural question to ask whether this equality can be realized. So they have Dunfield and Hirani have done some experimental data. As you can see, if the data is 1, then this equality will be realized. So equality will correspond to 1. And then what they obtain is 1.006. So it's very, very close to being realized. So that's a natural question. What I prove is that this cannot be achieved. The tool I use, or you can say that the obstruction I found are threefold. So for equality to be realized, the first obstruction is that your L2 harmonic one form, which realize the harmonic, which realize this equality must have constant length at every point. So basically, it is like the toric case I said earlier, where this black torus. So basically, this black torus, this torus over here, dual to dz, right? This guy has constant length equal to 1 at every point. It's a unit cube, and so everything is very unit volume. So everything is like very easy to compute. So basically, you are saying something which is true in the flat case should be true for the hybrid case. And the second property is that surface, let's say genus G, dual to alpha, should have area actually equal to the lower bound. So remember, the pi times Thurston norm less than or equal to the least area norm give you inequality. But to get equality here, you also need equality for that inequality. So remember that inequality pi times Thurston norm less than least area norm. So basically, you need equality in this inequality relating the Thurston norm and the least area norm. The last one is that your L2 harmonic one form is L1 norm, which is an integral, is actually equal to the infimum among the representatives cohomologous to your harmonic one form. So what I prove is that the second one, the first one is not possible. Basically, if you take L alpha harmonic one form constant length, this is inspired by Daniel Stan's paper 2019, using Bachner formula, the gradient of my harmonic one form is also constant length. And then this gradient of harmonic one form divided by the norm of my harmonic one form restricted to the surface dual to alpha is the second fundamental form of the surface. This is not true in general, but depends on the fact that harmonic one form has constant length. And by doing a computation, you can show that the second fundamental form is identically non-zero. Now, this contradicts a property of holomorphic credit differential because the second fundamental form of a minimum surface inside a hyperbolic three-manifold is the real part of holomorphic credit differential. This observation is due to Uhlenberg. Sorry, this is discussing Uhlenberg, but it's discovered like more than 100 years ago. Then now this fact that it's holomorphic credit differential will give you an obstruction because a holomorphic credit differential on surface with genus G would have 4G minus 4 zeros. So in particular, non-peripheral surfaces, you are ruling out those tori. Non-peripheral surface, those hyperbolic surfaces with genus at least 2. So in particular, this one, so you have 4G minus 4 zeros, but harmonic form with constant length would give you a non-zero, identically non-zero harmonic form. This is a contradiction. You can also appeal to Martin Rosen 2017-2009 because they tell you that this area, so here, this area law bound cannot be realized. So this one cannot be realized over here. And then if we go back, what I also prove is that a harmonic form of constant length would also imply that the area of S is equal to 2 pi G minus 1. So the first one is also an obstruction for the second thing to be an equality. So Wolf and Wu, the next approach is by Wolf and Wu. They define a notion of geometric foliation. So you can think of the geometric foliation is a foliation where if you go in normal direction, the variation is described locally by the principal curvatures. So it's some geometric condition on your foliation. So basically, a harmonic form with constant length would give you a notion of geometric foliation, such as this f function. This f describe how you vary it depending on your principal curvature. This f is identical to 1. So basically, a harmonic form with constant length would give you the best possible geometric foliation. So in particular, this is proved to be not possible. This is also published last year. Right. Okay, the last proof is dynamic. So this point I already discussed that the harmonic form with constant length give you a geometric foliation by minimum surface, but dually they give you an orthogonal geodesic flow. But geodesic flow is not possible by classical work of Zach-Heap from 83 because on closed hyperbolic manifold there's no geodesic flow. In the non-compact case, what you have is that this y go to infinity, your form would decay. Remember, this is finite volume one. Finite volume would decay like big O of e to the minus lambda y. Now, to get equality for the left-hand side, this must be harmonic form must have constant length, but then it decays, so it cannot have constant length. So this would contradict the constant length properties. Okay. So it actually has some application to a conjecture in broken downfield about the asymptotic rate of the L2 norm over certain norm. So basically, what I prove for the cusp case is not only inequality for the cusp case, but it's also model for when you have a sequence of closed manifold converging to a cusp manifold. What should you expect? So I don't have time to discuss the detail. It's almost 25 minutes. But then, so basically, using the inequality, you can prove that. So the conjecture it should blow up like this, but for one cusp, when M has one cusp, using the inequalities, you can prove that this guy L2 over a certain norm is bounded by a fixed constant. Okay, I will stop here. Thank you very much. I look forward to talking to you in the office hour, and I want to thank the organizer Okay.